Hello, everybody. Um, Let me just check, make sure everyone can hear me before I continue any further. Um, Face is a bit small there. Let me make that a bit bigger. I've just sort of updated my streaming stuff, as you can tell from the little chicken screen at the beginning. So I've just added a new starting soon screen, and I also have a new be right back screen for the break in the lecture as well. So this week, I guess we've had a few little things happen in the course in terms of assignment one. I think some people will have their final marks in assignment one, but most people at the moment will only have the automated marking, which is similar to your auto tests, but obviously they won't be exactly the same as the auto tests because we don't want people just writing a series of if-else statements for input and output. So the marking tests how well people are actually able to implement what was specified in the stages. So if you haven't had a look at that, the course website has a section in the menu saying view marking and auto tests and stuff, and you can go in there and you can see your marks. Over the next week or so, the tutors should be finished by this weekend. You will be receiving hand marking for the assignment as well, which is your tutor actually reading through and deciding how well everything has been crafted so that a human can read it, which is actually very, very important, right? So this is something that not only helps your own development so that you can understand your code and modify it, but also helps when you're working with other people. So your tutors are going to give you some feedback on that and some marks on that, and that'll be happening probably by the end of the weekend. We'll have all of the assignments marked like that. Yeah, and the other thing is we have released assignment 2. So I saw already someone saying help with assignment 2. Um, don't worry too much about assignment 2 yet, because a lot of the things you need to know about to be able to finish assignment 2, you still, I think, need a bit of what we're teaching this week to be able to complete it entirely. Oh, people like the Pokemon idea. Look, as much as I would like to continue doing the Pokédex assignment again and again and again, it gets a bit stale if we continue using the same assignment. And also, as you probably know by the fact that a bunch of people know about the Pokédex assignment, that the more you repeat the same assignment, the more it ends up on a whole bunch of websites online and stuff, and then people just copy paste from those instead of doing the assignment itself, and that's got like double badness because one, you don't learn anything, and two, if the more times the assignment is publicized online, the the more likelihood it is that people are going to use it, and then we end up having to fail people for cheating and stuff like that, which is really bad. So we try to refresh these as much as possible, and every time we refresh it, we're going to change the theme so that it's different, and so that the context of what you're doing is different. I'm not going to talk too much about assignment 2 right now, because I think I want to talk about what's going on in the background, like the theoretical idea of how to work with linked lists, before I go too deep into what the assignment is. So I had a live stream planned for Friday. I'm probably going to move that to Thursday, because realizing that Friday is a public holiday, meaning that people might not necessarily be wanting to work on Friday. Not like you've got anywhere to go or anything like that. The usual sort of going away for the 4-day weekend or something like that, it's not going to happen, right? Because we're all just stuck in our homes. But it still might be something where, I mean, if people are going to church for Easter, well, not going to church, but I don't know if people are live streaming churches. I'm assuming people are doing that. Like, I don't really want to be trying to live stream you content that you need for your course in conflict with your religion, so it's a bit awkward, right? So I might try to do that Thursday instead. But if I do reschedule it and pick a time on Thursday to do it, I'll send out a course notice, so you'll get an email of exactly when I'm going live. for the live stream. And if not, it's recorded anyway, so you know you can you'll be able to see it afterwards. It'll be similar to the stream I did for assignment 1. We're going to talk through the spec and talk about what it means. I'm going to give you some hints on what kind of structures that I think ought to be used in it. I mean, the hints are in the spec as well. We've got some diagrams in there also. It's all about linked lists, and I think it's better if you've seen this week's Tuesday, Wednesday lectures before you before I talk about the assignment itself. So the stream's going to be after the lectures. The other thing this week is that tutorials and labs have a whole lot of support for the second assignment. So there's a lot of stuff in there which is, it's nearly like freebies in there which are going to teach you. I mean, it's not freebies. It's like, these are the stuff we want you to learn. And in the assignment, you show whether you've learned it or not. So we're going to teach you stuff which we think is useful. So a lot of the stuff about linked lists that is in this week's tutorial has a lot of context for how you might put together the early stages of the assignment. So hopefully all that stuff helps you out. James and Sam are asking a little bit about what time on Thursday. So I usually have some meetings on Thursday that I have to be at. So it's definitely not going to be before 1. Considering my last meeting is 12 to 1, I will probably take a break for lunch. So the most likely time is going to be mid-afternoon, so I'll start around 2 or 3, I think. I'll try to offset it a bit so that I am not going over the space where too many tutorials are happening, because I feel like you should be in your tutorial. But no matter what, the live stream content is recorded, or the tutorial content's recorded as well. But I think the tutorials are where you can actually go and explicitly ask questions of your tutors, and so those are times that I think are more important than something like the live stream. So no matter when I do it, I would still suggest going to your tutorial. Should also point out something else that I was going to talk about. The public holidays that are happening. So I did send a notice out about this, so if you need it all in written detail, it should be in your email inbox or course website. Public holiday Friday and public holiday Monday. No tutorials or labs will be running on the public holidays on the Friday or the Monday. Anyone who has a scheduled tutorial on the Friday or the Monday, there will be a week 11 tutorial. However, as much as there is a week 11 tutorial, I strongly suggest you go to someone else's tutorial this week. Because if you go to another time slot this week, then you will get the assignment prep tutorial and lab at a good time. You'll learn the content at the right time, as in you'll be learning about linked lists that we introduced last week. You're learning about them this week, because if you skip it this week and you don't go to a lab or tutorial, you're going to end up kind of like 1 week behind on all the exercises and things, and I don't think that's a good idea at all, especially because like all the lab content, we're still going to have the same due date, so it's still released this week and it's going to be due at the end of this week. So if you can't make it to your Friday tutorial, if you're scheduled on Friday tutorial this week, and obviously you won't be able to go to that because it won't be running, please go to one of the other ones. So anything this afternoon, tomorrow, or Thursday, all of those are running. Especially because we're digital now, we're not limited by physical seats in rooms. You can go to any tutorial you want. So I think it's definitely worth doing that. So go to one of the other tutorials. But on top of that, anyone who doesn't have a tutorial this Friday or next Monday, your tutors will be running a bonus tutorial on the Mondays and Tuesdays of week 11. That tutorial will not be the content from this week, because that content will kind of be stale by then. You should already know that content. That tutorial will be a bit of a revision, so that will be like having your sort of own private help sessions where you can go in and ask about what you want to study for the exam, ask your tutors to recap certain things. Each of the tutors that runs a Friday or a Monday tutorial is going to be running one of those on the Monday or Tuesday, and those will be basically exam revision tutorials. So it's kind of like nearly that the public holiday has allowed us to run a bonus study session in week 11, which is going to allow you to sort of ask those final questions of your tutors and get a little bit more info and things like that. Yeah, as Tom's saying, I don't think there are any classes on Friday. So it just depends on how exactly your lecturers and other subjects are, how exactly and seriously they're taking the public holidays. Because I mean, it's just a really weird situation, right? Because I've never been in the apocalyptic calendar before, where it's just like, what day of the week is it? I don't know. I'm still at home. You know what day of the month is it? Oh well, I guess we're still counting these things. And like daylight savings just kind of came and went, and I hardly even noticed that the clocks had changed. If we hadn't had this weird stream scheduling change where I think it flipped my stream to like act like it was a 10 a.m. start. And I think that was a daylight savings thing. Someone was saying that may have been a daylight savings thing. It could also have just been me putting in the wrong time yesterday when I made the stream. So I was like, I don't want to start 9 a.m. And instinctively I made it 10 a.m. instead. I don't know if that happened. Yeah. Some people are saying the maths might even be having a test in the morning. Anyway, so hopefully that's enough information about the tutorials and labs happening Friday and Monday. If not, course website, hang on, let me just... Here's the notice that I put up on the course website saying public holidays coming up 10th of April this Friday, 13th of April next Monday, both public holidays. You can go to another tute, check the timetable for that. Timetable's here. Oh, we've still got our Stream B lecture there. I mean, it doesn't really matter now because we're not in those rooms anyway. But these are all of the times that there are lectures and tutorials, so there's heaps of them. I mean, if you really want to, you could even potentially, not all the tutors are teaching 2 tutorials, but there's a chance that your tutor is actually taking another tutorial at another time, so you can follow your tutor around. Or you can go learn from someone else, because getting a different person's viewpoint on things also is nice. So, up to you. But yeah, there's heaps of other time slots during the week. So there's always Thursday, Wednesday, Tuesday. So these are the ones that are still to happen this week. For anyone who's in a Friday tutorial, you can hop into one of those, and then you can get all the tutorial content that you would otherwise miss because of the public holiday on Friday. So hopefully there's a time slot that works for everyone. If there isn't a time slot that works for you, I suggest grabbing the recordings from one of these, because I think a lot of, especially the Monday tutorials that have already happened, a lot of those are going to be recorded. So if you go into Blackboard and you check all of the other tutorial time slots, you might be able to find one of them that was recorded. Okay, and also there is a catch-up lab. So anything that was on the 10th of April, so anything that's on this Friday, will have a catch-up lab on the Tuesday, the 28th of April, which is week 11. It'll be in the same time slot during the day. And the Monday labs will just move to Monday. Okay. Let's get into what we're talking about. Tom's in here spruiking his own tutorial, so he wants you to go to his tutorial. I mean, you can go to Tom's tutorial, but like, just depending on your time frame, you can go to any tutorial. Okay, so what were we talking about last week? Last week we did lots of little things and some big things. So we were talking about memory allocation. I can't remember whether that was last week. I mean, I did make these slides a couple of days ago, so I'm pretty sure this was last week's stuff. We were talking about memory allocation. So we're talking about the idea that we can grab a chunk of memory somewhere, and that memory is not necessarily going to get sort of thrown away when the curly brackets end. So it's not memory that's assigned to a particular function, but it's memory that's assigned to the entire program and can be reused and things. So the idea that we can make memory that lasts longer than the function that created it, and that means we can use functions to create data, stuff like structs, and then we can build up more complicated data with that. We also learned that if we leave that memory allocated, it's not going to go away on its own, which means we're going to use up memory. In essence, we're going to lose memory if we don't keep track of where it is, and that's what's called a memory leak. I think we have a demo of a memory leak in the tutorial. We did a demo in the lecture as well, if you want to go back and watch that again. We looked at multiple file projects, and that was a bit of an intro into what's happening this week with the second assignment release. Is that the second assignment this week is in multiple file projects. It is in a multiple file project. So there's more than one way to compile this. There's actually more than one main function in it, so you can compile one or the other of the main functions. I'm not going to go into too much detail in this because I'm going to do this in the stream about the assignment itself. But you can always look at the assignment, look at the spec. I suggest actually checking out the assignment spec before you go to your tutorial so that you have at least a vague idea about what you're going to talk about in there. So those multiple file projects. We covered command line arguments as well, another reasonably small topic, but it was the idea of how when we type in our actual program name, we can type in some information afterwards. And the information that goes in afterwards can actually be accessible to the program. So that information can be some text or some numbers, and it all goes into the program as strings, and then we were manipulating those strings to put them in the program. So the simple way is just to use them as strings. We also looked at one function that could turn a string into a number. Slightly complicated function. I mean, it's one of the more complicated library functions because there's actually pieces of it in there that we're going to ignore for the scope of 1511. If we were doing things at a more complicated level, that we were using this to pull parts of numbers out of a string while leaving letters in a string and do some other stuff, then we would use more of it. But for the moment, that was a simple way to say if someone types in numbers in the command line, we can use them as numbers. So that's not a bad one to remember and think about using at some point. Then we looked at linked lists, and we are going to definitely be using linked lists a lot. Linked lists as the idea of a node with some information and a pointer to another node with some information, another pointer to another node with some information, that kind of thing, are really one of the fundamental data structures in computer science. So from the idea of linked lists, we can build up the idea of what's known as graphs. So a graph is nodes that point at multiple other things, and so you can have nodes pointing at other nodes and things. You can actually get like a data flow. Have you ever done one of those diagrams which is like, should I do this or this? What's the information? Is it this or this? And it forks and goes in different ways, and then it forks and it goes yes or no. Should I do this or that and stuff, like the funny ones of like should I go outside during the coronavirus outbreak, and it's like the yes or no always ends up being no, you should stay at home. It's like, what if I want to see my friends? It's like, no, don't do that, you're going to infect them, go home, and all this kind of stuff. So that kind of yes or no decision diagram can be done via a structure very similar to linked lists. And when you get really deep into it, the core structure of neural networks is based on the same kind of thing. Nodes with a certain amount of information in them that then link to other nodes, and so you follow the chain through something like a neural network, and you go from information that goes into information that comes out. And at the moment, they're one of the more famous forms of artificial intelligence that's in use nowadays. So what we're teaching you now is kind of one of the fundamentals that builds up into all of this kind of information. So that's kind of what linked lists are. Tony was asking, is the assignment the final tests? No, there's an exam as well. There's going to be a 24-hour take-home exam. We need to actually sort of give you a bit more information about what that's going to be. I am definitely going to dedicate some time to that. Whether I do that in a live stream or in the lecture will depend on how much content I want to deliver in the lectures and how much time there is for all the lecture content. As it is, I think I need the lecture content for teaching you about the actual theoretical concepts that you need, rather than spending a lot of time on I guess what you call admin, or telling you only about how to pass the course. I tend to want to have the lecture content focused on the actual techniques you need, and then little bits that are specific to the course itself or specific to the assignment, they get pushed out into the live streams. So I want to make it so that if someone only views the lecture content, then they'll have all the theoretical content they need. And if they want the content that's like a little bit specific to things, it'll be on the other parts of the course. All right. So today, excuse me, I also only woke up just in time to deliver this lecture, which is, I think, what a lot of people are doing at the moment. We're going to continue our work from last week today. So last week we started on linked lists. So we learned what linked lists were. And we sort of started building one, and we learned how to loop through one. And I drew a lot of diagrams. I didn't draw the diagrams. I showed the diagrams in my slides. They were all going to help you understand I guess from the theoretical side, what a linked list is. And today we are going to build up an example that I'm going to work on through this lecture and the next lecture, which is going to be an example that uses linked lists. And we're going to learn about inserting elements into linked lists, and then we're going to learn about removing elements from linked lists. So what I'll probably be doing is focusing on the insertion today, so to add nodes to a linked list, and then tomorrow we're going to focus on the removal of nodes from a linked list. And hopefully we'll be able to complete the entire example in these 2 lectures. We'll see how we go, because I'm finding actually that the lecture content we're going through a little bit slower at the moment in the live stream, because I go over to the questions and I answer people's questions as we're going through. So it means we're getting through the content a little slower than I planned, but I actually find it a better form of lecturing than my normal lecturing. Because normally when I lecture, I just deliver. And you don't necessarily get to ask questions, because you have to put your hand up to ask a question. I have to pause everything to answer the question and stuff. Whereas this format, your questions just appear in text there, and you can have discussions about things. And if I look over and I see something I think that I should present to everyone, then I present it to everyone. So I actually find that the slightly more interactive way of teaching like this might be superior to the standard lecture. We'll see if I can actually make that happen in a more permanent way in future lectures. I started off with that with stuff like Slido at the beginning, but it was just so much spam. There's just so many people posting random stuff on Slido that I was like, oh, I stopped doing that. But for some reason the live chat here seems to work. So I don't know. Maybe it's because after we went online, there's not as many people in the lecture at the actual time it's delivered as there used to be, because there's about 100 of you here now, whereas if we were in-person lectures, I think there'd be about 400 or 500 people, so it would be slightly different. I don't know, but for the moment I think this is okay. So recap, linked lists, and you know that I was going to throw at least one meme in there, so I mean it's basically my face anyway. I keep wanting to do a cosplay of this guy, because it would be so easy. All I need to do is get this awesome leopard print suit and not shave my mustache for a couple of days, and I could just be this guy and just go around and dance and stuff. So anyway, I'll put my face over his for the moment. So recap of what linked lists are. Structures like this node here that holds a certain amount of specific information. There are 2 things that it will have. One will be a pointer to another structure of the same type as itself. So that's how we get nodes attached to other nodes, and each node carries some information as well. For the moment here, it's just an integer, but because this is a struct, obviously our nodes can carry a significant amount of information. For example, our nodes could be a musical note with the pitch that the musical note is, or it could be, I don't know, the example I'm going to use today is it could be a player in a game. So those little silly examples that I'm using all the time of games, we're going to do another one of those today. So the structure is always a way to connect the structures together, as well as some information that the structures are actually carrying. I will get my face out of the way up there. Okay, so this diagram is one that you're going to see a lot. I use the same sort of diagram format for pretty much everything in linked lists. Sorry, it just got really bright and glary in my room. I'm just going to try not to bump the camera too much when I do that. Okay, I just needed to get the glare out of my eyes. I have a window behind the camera there. So the linked list here, each of these nodes has a next pointer. The next pointer allows us to access another node, and the data is the information that's actually being carried in it. So we had a quick look at this, and we looked at it in code and how it used these kinds of structures, and then we had some code for how to loop through a linked list. So the fundamental idea of looping through things that we used with arrays we're using with a number. So we're using an index to access each element of the array. Now that we have a linked list, there is no sort of fundamental index that is going to allow us to access each element of the array, but we can go through the array one at a time, and we do that by having a pointer aimed at a node, and then that node tells us where the next one is. So its next pointer says, hey, go here next. So we go, okay, that's the thing we're going to next. We move our pointer to the next one, and then we move our pointer to each one as we go along. And that's what this basic loop structure is here. So we start off with a pointer, and we're going to assume in this function here that the pointer that we were given at the beginning of this loop was pointed at the head of the list. We call the head of the list the first element of the list. And so if we have a pointer to the first element of the list, we have a while loop that says keep going until that pointer is null. Because if we remember, the final pointer in the linked list points to null. So the first pointer is a pointer to the first node. This is what we'd call the head pointer here. And us looping through is to say that if you're not null, it means you're aimed at a node. Then you can do something with the data that's in the node. So here we're going like n.data, n spike data here. And then after we're done with that, this is like our I++ that was moving us onto the next node. So moving us onto the next node is to say the n pointer, the thing that's aimed at the node. We don't want it to be aimed at the node that we're at now because we've finished working with it. We now want it to point at the next one. So n next. So if I go into n with the arrow and find its next, it's pointed off at another node, and then I can go on to there to get to the other one. So this basic function here, we're probably going to use this a fair bit. So this is the basic thing that's going to loop through lists. We're going to use this just if we need to see every element in the list, because we're going to start from the beginning and then we're going to go to the next, the next, the next until we reach the end. We're also going to use this in more complex ways, and we'll see some of that today if we get up to it. When we're inserting, we're actually going to be doing some interesting things with looping through, because we can sort of keep some data with us as we loop through. As you know, with arrays, if we wanted to loop through an array and keep some information about what we've seen and where we've been, we can keep that in our loop or in variables that are outside our loop. What are we saying? We need a semicolon after the closing brackets. Did I forget something? I did. Apologies. Let me go back to that. You just wanted me to go back to the PPAP slide, didn't you? Okay. So this is our loop. Let's go into what we're actually going to build up today. So the next hour and a half, we're going to put together a battle royale. So this is something that I thought would be pretty funny because everybody knows Fortnite, right? I assume everyone knows Fortnite, or has at least heard of it. It's like the biggest gaming thing that's happened in the last, I don't know, 2 or 3 years. Or even maybe a bit longer than that. The whole idea of the battle royale genre of games that's come up as being like the biggest thing out there at the moment. So if you don't know how a battle royale game works, the way it usually works is 100 people get put into a map together, like a big map of players, and all the people are there, and they're all having a big biffo, so they're all fighting each other, and everyone gets knocked out until only one person remains, and that person's considered the winner. And the way the battle royales work is they tend to shrink the area you can play in, so if you're outside the area, you get killed. And in the end, it just sort of forces everyone to fight each other until there's only one person left. We're going to use linked lists today and tomorrow to work with the idea of a battle royale in terms of a player tracker for a battle royale. So we're going to have a struct for a player, And using the struct for players, we're going to put different people's names in, and then we're going to track who's in the game. So the first thing we want to do is start by building up a list of everyone who's in the game, and then we're going to want to be able to knock people out of the game. And this is something that the linked list is very very well suited to, that the array is not so much. Because if we want to have a game where, you know, every now and then someone disappears from the game, we want to remove single elements from this list while having it sort of remain a viable list. If I was to do this with an array, it'd be really awkward because I'd be like trying to leave gaps in the array, or I'd be trying to shorten the array, which means I would have to like destroy an element of the array and then move everything in. It's really messy. So the linked list is really nice because just by moving pointers around, I can remove things from the list. So that's something that's going to be quite nice. And also, if I don't know how many players are in the game to begin with, so maybe it's not a full 100-player game or something like that, I can build up my linked list. So linked lists work really well for a list that's going to change its size a lot. Because the arrays don't change their size, whereas the linked list can just happily grow and shrink at any time. We're not going to be growing this list quite so much because of the particular way these games work, but shrinking it we will by bits. So, things that we're going to do. We're going to start by adding players to the game. So this means we need to have player nodes and we need to construct our linked list. We want to be able to also print out all the players that are currently in the game. So we want to be able to say who's in the game at the moment, someone got knocked out, who's left, you know. So we have a listing of who's left in the game out of the people who are still available in the game. The other thing we want to do now is we're not just going to build up the list, but we're going to add in the idea of being able to keep this list in order. So I'm going to work with an alphabetical ordered list. Some people might have heard of things like sorting algorithms. Sorting algorithms are pretty famous in programming. They're the idea that you can take a list that's out of order and move things around so that it becomes in order. A whole lot of work has been done in programming over the last kind of 50 years on getting sorting algorithms to be the best they can be, so they can run the fastest or they can use the least memory and stuff like that. We're not really worried about sorting algorithms yet in 1511. We think you need the data structures first before you can go on to learning to sort them, so we need to just sort of chill and just actually understand linked lists first before we think about jumbling things around too much. So what we're going to do is we're going to say every time we add something to the list, the whole list is going to be in order. So an empty list is always in order because there's nothing in it. And then every time we insert, we're going to try to insert in the right place to put things in order. So that way we're going to maintain an alphabetically ordered list without having to go through any particular sorting algorithms, which we really don't have time in 1511 to teach you that. You're going to get into that in later courses. Because for the moment, I think it's enough pressure to learn how a linked list works at all, let alone going into that deeper level. The other thing that we're going to want to do, and this is something we're definitely not going to get to today, but we're probably going to be doing tomorrow, is how do we remove players from the list? So if I was to say two people met in like a house in a forest somewhere and they got in a fight and then one of them got knocked out of the game, I can type in the name of the person who got knocked out of the game, for example, and we have to be able to go through our list, find the person that was knocked out of the game, and remove their structure from the list. So that is going to be the idea of like how do we loop through and find something, and also how do we remove something. So by the end of this example, so this is going to be like this entire week's worth of work in the lectures, by the end of this we're going to be able to build lists, we're going to be able to insert nodes into lists in a particular position. We're going to be able to find that position by looping through the list. We're also going to be able to loop through a list to find some particular thing in the list, and we're going to be able to remove elements from the list, which is going to include the memory management that we need to remove things. And so by the end of this, you should have all the basic capability that you need to be able to work with linked lists. Again, as usual, don't worry if this doesn't 100% sink in right now. We do have a tutorial and lab next week in week 9, which is like because the lectures are entirely linked lists. This week, the tutorials and labs are going to be entirely linked lists next week, and we'll look at insertion and removal. We'll look at looping through lists and stuff like that. So this week it's going to be a little bit easier because there's no removal yet, and the insertion is only at either end of the list, but we're going to look at inserting in the middle of the list and what the ramifications are of doing that and how to move the pointers around. It's a little bit complicated, but we'll get there eventually. Yeah. So people do know about Fortnite. I actually haven't really played Fortnite. Oh, and people are okay. So some people have learned about sorting algorithms and big O notation. All that stuff is like super important for computer science. But for anyone who's reading stuff in chat and stuff, don't worry too much about stuff. You'll learn it all later. And anyone who does know about that stuff, I say that BOGO sort is the best sort of all the sorts. I'm kidding, it's not. It's the absolute worst, but it's kind of the funniest. Okay, so how do we start going about building up this particular game? So in order to build up this, we need to start building up our structures. So we're definitely going to need a structure for the players. If we need a structure for the players, we're going to need to be able to join them together into a linked list. So I say that the structure that we're going to use for a player must be similar to the structure that we've shown for a node, which means it needs a pointer to another player. So it's going to look a little bit like this. I'm going to keep it simple and only put a certain amount of information in that, which is the name of the player. So we're going to have a hash defined somewhere, which is going to be the maximum name length that I'm going to use. And then I'm going to say that there's also a pointer to another player. So this is going to be our basic node for a player in our game. And I think it is about time to get into the code. Alright, so I've just logged into VLab here. Into my COMP1511 directory. I'm going to need to make a new one. Make a new directory here for lecture 13. Yeah, I don't have a lecture 13. Going to lecture 13, so that'll be empty for the moment. So I don't have any file to start off with today. I'm going to build it all from scratch. I won't bother calling it Battle Royale. I'm not going to call it Fortnite because there's other games that have that genre. I don't know if anyone used to play PUBG before Fortnite switched over to Battle Royale. PUBG wasn't even the one that invented this. I mean, one could consider that the idea of Battle Royale was actually created in... Was it the 90s? There's actually the movie called Battle Royale, which is a Japanese movie from, I think it may have been the 1990s, or at least the early 2000s. And it took the computer game industry a good 10-15 years before they decided, hey, we can make games out of this. This could be really cool. Anyway, so I'm just going to call it Battle. I can't remember if I've actually made another example called Battle before, but it's okay, it's in this directory, so it won't be the same. So, here's my C file. Oh, Quantum BOGO sort. Yeah. People ask me about like stuff like Minecraft, Hunger Games, and stuff like that. Did you know that CSE Society, the group of students running stuff, actually started their Minecraft server last weekend? I didn't actually join in. I knew people were doing it, but I was busy on Friday doing some other stuff. But there is actually a CSE Minecraft server, so you can get on there and hang out and stuff if you want. Okay. So let's start building up this file. First thing I'm always going to do when I create a new code file is make sure that I put a message in there for myself to remember what it is. I think this is what this is. It's a Battle Royale player list organizer. Keeps track of players in a game where they can be eliminated one by one. Also a demo of the basic functionality of linked lists, because I think this is quite important, right? This is about how linked lists are going to work, and so this entire example is going to be a whole lot of stuff which should show you the basic principles of how things work, and you should be able to take all this code that I'm writing in the next 2 days, and if you spend some time with it, if you've been able to kind of spend some time with tutorial and lab stuff as well, you should be able to actually adapt a lot of this code to use in your assignment. I should also point out that any code that we write in lectures and tutorials, or any code that we give you in the subject, none of that counts as plagiarism, because that's you using the subject material to pass the subject, which is totally what we're supposed to be doing. It's only if you have used someone else's material that already solves the problem and just sort of copied it that we consider that to be a problem. But you may find that there are things that we will give you in lectures and tutorials and labs and live streams, which you will understand that with a slight amount of modification will work very well for your assignments. And that's really the key when we give you material, is we want you to be able to see this part of the material works for this part of the assignment. This is the way that I want to modify this for it to work in the assignment, and if you can do that, then we consider you to have understood what's going on, which is the most important thing. And you'll find that a whole lot of professional coding is like that. A whole lot of times when we're doing stuff professionally, we don't invent stuff from scratch. We're going to go through and we're going to say, hey, someone else did this thing and it works for the kind of thing we're doing, but we need to make some changes. So let's have a look at what they did. Let's get a good understanding of it, and let's change what we need so that it works for us. That kind of thing is a very professional way of programming. So this is the kind of way that we're just kind of slowly lead you towards the idea of how to do things in a completely professional sense. Okay, so the struct that we were making, I was calling player. So the player struct is something that represents one person in the game, which means they're going to have a name, and that's going to be an array of characters. For that to be an array of characters, I'm going to need to specify a length in here. So if I'm going to do that, I'm going to define a length. Was it max name length? I think it was max name length. I could have had max length there. So let's say that the max name length is not going to be that big, because it's just the identifier for a person in a game. Ooh, 1,000's a bit much. I very much doubt someone's going to have 1,000 characters in their name. So a max name length is there. Things we might need as well. We're going to need to include some things. So I'm pretty sure I'm going to need my standard input-output library. The other thing I'm going to need if I'm going to do memory allocation is the standard library. And you may have noticed in the starter code for the first assignment, we had the standard library in there, even though we never used it in the first assignment. That's because an experienced C programmer on Instinct will just usually include both of these and then go on, and then maybe not even use them. But we tend to include these all the time because they're nearly always going to be used in most C programs. So in the same way that standard input-output library was something that I gave you from the beginning and that we're always using, because if not, we wouldn't be able to see anything in the terminal, the standard library is something that's potentially even more fundamental, because the standard library is going to be used anytime we're not even using the terminal, if we're opening a window and using a GUI and stuff like that. We'll get into that stuff later on in your degree. We're probably not going to be doing anything at that level. We're definitely not doing anything at that level at 1511, because it just, again, introduces massive levels of complexity. And at the moment, we're trying to work on the fundamentals, not all the other stuff that's added on top. But yeah, so this is the includes that we'll have in nearly all programs now, is the standard library is going to end up being there for most things. I'm sponsored by Fortnite. Mega Abominator's interesting question. Are linked lists used more than arrays, or are they both widely used? I would not be able to say statistically which one's used more than the other. I would say that potentially arrays are used more than linked lists, but that's because linked lists are a particular form of node and pointer structures. So the whole node and pointer structures are used heaps. So there's a whole lot of ways of doing these where you could have, let's just actually finish this. This is going to have a struct player pointer in it called next. If I wanted to, I could have more of these in here. So I could have ways to link to multiple different things. Those things are used a lot in computer science. I don't want to do them now because it's complicated enough getting the linked list into the human brain, let alone a multiple node structure that we'll get to eventually. I mean, it's really easy to draw this. You can draw a bunch of circles on a piece of paper and draw lines in between them and go, okay, all these things are connected together. It's like a map, right? You could have cities and roads between cities, and that is nearly like what a linked list structure is like if we were to expand it to have multiple pointers. So it's hard to say which is used more if you include those as the idea of linked lists. They have different purposes. Experienced programmers, which you will be eventually, will be able to decide based on the context of what you're working on which of these you're going to use. Yeah, and also different kinds of data. These aren't the only data structures either, because there's actually arrays that can change their length in different languages. You may have heard of vectors. And so they can have some of the capability of linked lists and some of the capabilities of arrays. And the more you go into things, the more you'll learn the pros and cons of everything. So what we're learning at the moment is the difference between a linked list and an array. So this particular example will show you something that works quite nicely for a linked list and is really awkward to do in an array. And in the coming weeks, I'm actually going to end up showing you some more things which are about ways to build abstract structures, ideas. So the same way as like the assignment, so Minesweeper was like, we've got a two-dimensional grid. And so if I tell you, make me a two-dimensional grid, your first idea might be, okay, two-dimensional array is going to work pretty well for a two-dimensional grid. If we wanted to, we could have a two-dimensional linked list. It's fiddly, but it's possible to do a two-dimensional linked list and run your Minesweeper assignment on a two-dimensional linked list instead of a two-dimensional array. And that doesn't change the square that the minefield is, the field itself. It doesn't change how it works, but it changed the underlying data structure we used for it. And the decisions we make to decide between the data structures are always going to be our own decisions as the programmer to decide which one we think is going to be most appropriate, which one is going to have us writing the least amount of code to have these operations work on it. Or when we get to more advanced levels of programming, which one of these is going to have the least sort of use of memory of my system, because I think the memory needs to be used for other things in a larger scale project. Or which one of these things is going to burden my CPU the least, so which one's going to do the least amount of work for the computer. And these kinds of decisions are the things you're going to come up against a lot. And you'll find that in computer science, you know how I said we have these two things in computer science? You got the thinking bit and the remembering bit. And we're going to burden both of those. So we're going to be using the thinking bit to make decisions. We're going to be using the memory bit to store our information. Both of those are finite. You know, one of them has a certain amount of things it can do per second, and the other one has just a certain amount of bits that it can store stuff in. We will often be going back and forth between the two. So sometimes we can use our processor more and use less memory, or we can use more memory so that the processor's working less. And that kind of trade-off is something that you're actually going to see a lot in computer science. There's plenty of ways that we can use more memory to use less processing, or more processing and not have to use as much memory. And depending on the actual situation you find yourself in, you're going to be choosing between those things. This is all in the future, by the way. At the moment, we're not doing anything like that. At the moment, we are focusing on the much more important thing of does it work and getting your code to work, which one must do first before one tries to make it run faster. Like, there's no point having something that you've spent a whole lot of time trying to make it run fast if it spits out the wrong answer, right? So we're going to go for right answers first. Okay, let's get back to my slides here. So, we have this structure now, which has the name of the player and a pointer to the next player in the list. So, if we want to create players, we can have a function that's going to create the players. Now, this is in essence me doing a recap of what we did last week. So all the stuff we were looking at last week, which is like a superhero theme thing, this time we're going to be building all that code and having all of these functions built up from scratch. So what I'm going to do is I'm going to have a function that's going to make a new player. And this is going to be called create player. And it's going to get given a name that it puts in, as well as a pointer, and it's just going to fill out the information in the player with this information that we get given. I don't think we need to look too much at the code here. I think it's better if I write it with you. So, we have this thing is going to return a pointer to a player, and I'm going to call it create player. Should remind everyone that when we're doing these things that this is a type in the same way that this is a type. As we're building these things up, they get more stuff, but remember the star here is actually part of the type, and the star is not part of the variable name. So the variable name is create player. Create player is a pointer to the player struct. Well, it's not actually a variable name here, it's a function name, but the function is of this type, struct player pointer. Okay, so create player is a function that is going to take in a name, which is an array, and it's going to take in a player pointer. Did I name those the same there? Oh, okay. I'm gonna write these as new name and new next, just so that when I'm running this you can see the difference between the two. It's not entirely necessary to, sorry, I don't know if that traffic noise, if you can hear that. I'm assuming you can, because that one was pretty loud. Someone's asking, do we recommend you using typedef for all programs now? I wouldn't necessarily recommend it for all programs, but I would recommend it anytime that you're splitting things between files. You can use a typedef to not have to do this idea of the struct player pointer. This one's all going to go in one file for now. For this example, it's just about linked lists. But when you get into the assignments and stuff like that, and the stuff that we're doing in weeks 9 and 10, probably, yeah, weeks 9 and 10, we are going to do stuff there. We'll do more on typedef then. So I wouldn't worry about it too much now, while we're just trying to grapple with linked lists. But when we move on to the next subject that I'm going to talk about in the final weeks of the term, we'll talk about linked lists then. Okay. Okay, so this is our function. I might actually put my main function in here. Oops. You know when you look at the code you've written and you go, that looks incorrect. What looks wrong about that? It's like, what are you doing, Mark? The void is outside the brackets. Okay, nothing in my main at the moment, because that's going to be the thing that's actually going to run. I'm going to build up some of the functions I need before I put anything in my main. So, this function, create player, I'm going to copy this, paste it here, just put some white space on working in the middle of my screen here. Okay, anytime I create a function that's going to be used elsewhere, I need to talk about what it is and what it does so that I remember what it is, because it's out of order once it's at the bottom of the file, and so I don't always know the context for what it's going to be. Sometimes it's okay if this is really obvious, but it's not entirely obvious what the return is or exactly what these inputs are going to be. Create and allocate memory for a player struct return a pointer to that struct. Okay, I think that's enough information. What I like to do usually in any comment that I'm going to put for a function is say what it does, and if it returns something, be specific about what it returns, so that someone's using it can say, okay, this is what I'm getting back, this is the type that I'm getting back, but up here I have some information about exactly what it is. Okay, so to make this, we're going to start off with creating a pointer. So struct player pointer, we know we have to make one, because if we don't make one, we won't be able to give one back. So we're going to have to make something of this type here, exactly the same as the type of the function, so we can return it. I'm just going to call it P, because at the moment this player doesn't have a name, and this pointer is really a temporary variable. I guess if I wanted to, I could make it really specific with something like new player. I'm always going to kind of go back and forth on these things. Sometimes when I have a temporary thing, I would go easy on the variable name, but maybe while I'm teaching this, I should specifically use good variable names for everything. So, pointer to a new player that we've created. This is going to immediately be assigned to something. So I need to assign it an address. The address I'm going to get is the address of the memory that I've allocated for this. So I'm saying I'm allocating memory, so I can get an address to that memory to put in this pointer. I'm going to do that with malloc. Malloc is my memory allocation. Malloc wants to know how much memory that I need, and then my computer is going to, after being given that amount of memory, is going to tell me where it is. So I'm going to use size of. Size of is going to allow me to say this is how much memory I need. If I wanted to, I could put in an exact value, but exact values are just fraught with danger, because I really don't know exactly how big something is going to be, because as I develop, things might change. So I might change from just having the name of the player to adding in other information, in which case this will change. So the safest thing I can do is say I need the size of a player structure. So this is going to look at this structure and say, how much memory do you need to store that structure? Well, you need this many characters, so that many bunches of 8 bits, and you need a pointer to another player, which is 64 bits. But I don't want to just add that up in case these things change. So if, for example, I'm working on a different kind of computer architecture, the pointer might not be 64 bits. So it's better that I don't put a number in here. It's better that I just ask what the size is. So this is the, as we looked at last week, this is the bog standard memory allocation line. You say, I've got a pointer, and I want the address of a piece of memory that I'm allocating, and the type here is going to be the same as the type here. So I'm doing a pointer to a specific type, I'm allocating memory for that same type, so that pointer matches the type that it's aimed at. So this is like, if you only remember one way to allocate memory and it's this, that'll be pretty safe for now, because this is nearly always going to be correct. Okay, so we've allocated our memory. If we wanted to, we could check whether that memory had allocated correctly, but as we saw previously, that if we don't allocate the memory correctly, it's likely to kill our whole program. So it's not always entirely necessary to check that kind of thing. Okay, I guess I did it differently here. I had it over 2 lines, but that's fine. Okay, so we've allocated that. Now we're going to put the information we've been given, the new name and the new next pointer, we're going to put them into this new player. So the new player is a pointer to a player struct. Oops. Because it's a pointer to a struct, it needs to use the pointy way to find the fields inside the struct, which is the arrow. This is the difference in the arrow and the dot. If I had a player struct, then I would use the dot, but since I don't have the player struct, I've got a pointer to the player struct, I use the arrow. So its name is going to be equal to new name. So remember, this is not going to work. Me trying to put a string into a string is not exactly how things work, because the string's an array and I can't just make an array into another array. So this is going to have to be a string copy. in order for me to copy one string into another, I need to know what this string copy function is. I have not defined a string copy function. I also don't have a string copy function in any of my includes here, so I'm going to need to include the library that uses that, that provides that, which is the string library. And if at any point you wonder about whether you have standard library functions for things, it can be worth actually looking up some documentation on the C standard libraries. So there's a whole bunch of them. The commonly used ones, there's about 6 to 8 of them. And if you look through those, you'll find potentially hundreds of functions. The issue is trying to figure out which of those is useful to you, and which ones you want to sort of memorize what they can do so that you can use them more often. The nice thing about this is there's nearly always going to be references you can Google for things like this. So if I said I want to be able to copy strings, and I was to say I'm not sure how to copy one string into another, I can just type into Google copy strings in C, and somewhere there's probably going to be some information that says, you don't have to do that yourself. If you were to include this library and use it, it would be fine. So there's always ways to look up the information that we need. Okay, the next thing we're going to do is make the pointer, the next pointer that's in new player, equal to the pointer we've been provided. And this one we can just copy over because it's not an array, it's not a collection of information, so we don't need to loop through it to make it work. Okay, so what we've done is we've allocated new memory for a player, assigned it to a pointer, populated that memory with the information that we've been given, so that player is created, and now we can just give back what we've been told this function gives back is a pointer to this thing that we've created. So new player is a pointer to the memory we've just created, so we can return new player. So not many lines of code, but this simple 4-line function pieces together a whole bunch of things that we've only just learned. So a whole bunch of things that we've only just gotten to. The idea that we can memory allocate something, the idea that we can have a pointer, which is a variable that aims at another variable, so it's a variable that stores the address of another variable. So here's the thing that we've actually created, this memory allocation, and then we have a player pointer that aims at that memory allocation. So we've got a piece of memory and a pointer that says this is how we access that memory. We've used a library here to copy one string into another. We're also using the arrow notation to follow a pointer to a struct to find the field inside that struct. So both of these, this is going to put the string in, and this is going to put the pointer in, and then we're going to return it. So in these 4 lines here, I'm nearly piecing together what would be about, I don't know, like 4 or 5 weeks worth of our learning, and it's really funny because it's just such a small function, but you need to learn so much to understand how it comes together. So I think this is a really nice bit of function to look at here like that, because it really does put it all together like this. We've got a couple of questions there asking about why we're returning a pointer to this thing that we've created. If we don't return a pointer to this thing that we've created, this variable here is the only thing that knows where this memory is. So it being the only thing that knows where this memory is, and it being a variable that will disappear once these closing brackets end, will mean that we will lose access to that memory and create a memory leak if we don't keep track of that pointer, which is why that pointer is being returned, so that the main function, if the main function calls create player name, it's going to be me, I'm going to go first, and the next pointer is going to be null because I have nothing else to point it at. If I run this like this, it's going to cause a memory leak because I didn't keep track of the pointer that came back out of it. But if I do something like struct player pointer head of the list equals create player, now I have access to the thing that I've just created, and I can do things with it as well as doing stuff like freeing it. Um, where there was another question about if we didn't want to use the library function. If we didn't want to use the library function, yeah, it's pretty easy for us to loop through. In fact, I think this may have been a lab question at some point during the term earlier on that was just loop through an array and copy it into another array. Um, if you were to do that here, that's exactly what string copy would be doing. So I could write my own function, which says copy one string into another string, and it would just while loop through until it hit the null terminator and copy one into the other. So yeah, we could definitely do that ourselves if we want to. And it's probably worth doing that at least once to learn how that works. Okay. I'm going to go on a break now because we're 10:05. Where's my break? There it is. Break time. Okay. I can't remember whether I've actually showed some of this information before. I have talked about a couple of these things before. So, homework in case you're bored at home, because we kind of can't leave our houses at the moment except to go shopping or exercise. Actually, if you're going to get exercise, leave your home to get some exercise on your own, not with other people. That's good. But if you're bored, there's other things. There's a lot of stuff around the idea of programming, computer science. A lot of stuff that we call science fiction, which I think is really, really interesting because it gets us thinking about what are the ramifications of what it means to be a computer science, and what are the ramifications of creating programs that are able to, at least to a certain extent, think for themselves. And these are some really funny things and really interesting things that you could look at. Human Resource Machine, I've definitely mentioned this before because it's a game that actually has you programming in the game. And it's kind of interesting thing if you want a little sort of time waster, which strangely enough is not actually wasting your time because it teaches you how to structure loops and things like that. And by the end of Human Resource Machine, you'll actually be a reasonable assembly programmer. Assembly is a language that's just one level more detailed than C in how it does things. Some cool things like the AlphaGo documentary on Netflix talks about the current one of the current big AI projects in the world. Well, I guess it's not that current anymore. It's like a couple of years old, but it's still worth watching. It's really interesting. It's about creating computer programs to play the game of Go. You know, the little white and black beads that you can put on a grid. Some books that are interesting to read. Isaac Asimov is, historically one of the most important sci-fi writers. Neil Stephenson is less historically, much more recently, a very interesting sci-fi writer as well. Some really cool stuff there that goes into some details about things. If you're into board games, I don't know if people are into modern board games. I'm not talking Monopoly, Trivial Pursuit and stuff like that. I'm talking about more modern, more specifically designed games. Space Alert's really interesting. It's a game where you program your little player to do things, and then you don't find out what they do until everyone's finished their programs, and then everyone flips all these things over to say, okay, this is what we did, and then you see whether they actually follow the program correctly or not. Super interesting for programmers because it reminds us that our code never works properly and always has issues the first time we test it. Anyway, let's go on break. I'm gonna make this break reasonably short because there's more stuff that I want to do, so I'm gonna take a 2-3 minute break. It's what is it? It's 10:08 now. We'll come back at just past, I don't know, 10:12 or something, 10:11, 10:12, sometime around then, and we'll keep going. Alright. And I get to show you my new Be Right Back screen, which everyone's going to love. Okay, here we go. All right, we're back. Chicken's actually in here at the moment. She came in while I was on break. Come on. All right, there you go. Little dose of actual chicken. Hello. All right. Okay, let's move on. Okay, we're gonna knuckle down and we're gonna write some code now. So let me go back to my slides and we go back to here. So we've made our function that creates players. And so now we have the ability to go through and make a list out of players, because all we need is the ability to put the data in the node and assign a pointer to the node, and we can start building up a linked list. So if I want to, this is the question of like, what's Mark been watching recently? So, because we're on lockdown and there's not much going out of the house and doing anything, I got myself a subscription to one of the streaming services. Probably shouldn't name brands too much, like, because it's not really something that I should be I should necessarily be spruiking brands and stuff. We always joke that I'm being sponsored by everything that I'm talking about. But I've been going back and watching the original Dragon Ball, like it's like 1980s, so it's this hilariously old school animation. So I've decided Dragon Ball, but to actually make it a little bit current, I've put myself and Tom in there as well as the subject, as myself and Tom the subject admin in there. But we're going up against Goku, Bulma, and Master Roshi, so I don't see how we're going to survive, but we'll see how we go. There is one way we can create a list in this really, really simple way with only a create player function. So you note that this first line here is something that I've already written. Where's my code? Over here. Something I've already written, which is I can create a list like this. This is a list with one element in it. Its next pointer is null. It is the head of the list. And if I want to, I can add another element to this list by saying there's a new head of the list, and the new head of the list is this new node that I'm creating, and the new node can have its own name, so Tom can join us here, and its next node, instead of being null, its next node will point at what used to be the head of the list. So I can say Tom's a new node that points at the head of the list, and then once this is done, I can say now move the head pointer to point at this. So the first list that I create is myself with a null pointer, and then the second list that I kind of create, well, it's not the second list, it's the same list. There's a new head called Tom, and then the next pointer points at what had been the old head. I got some diagrams for this to make it easier to understand. I'm getting in trouble for not putting JoJo. I know, yeah, okay, JoJo is like super famous, but one must consider my age, in that, like, if I'm going to talk about anime of my era, it has to be Dragon Ball and Naruto. Or if you want to get really old school about this, then I have to talk about Macross, for example, or Gundam, but like not even New Gundam, like Gundam with no extra letters after it. But let's not go too deep into that. Okay, so this is a way that we could build up a list out of, and also I want to make it like actually what I'm doing at the moment. I don't want to just like have random references for things that I'm not actually doing. This is what I'm actually rewatching at the moment. So I'm watching the old episodes and they're hilarious. It's much more of a comedy back in the actual Dragon Ball, no Z or anything, just Dragon Ball days. Anyway, this way of structuring the list means we can make a new node that aims at the current head of the list and make it the head of the list. Diagrams to show how this works. So, when I created my my list originally with my name in it here, actually, you know what? Let's I can edit these as we go along. So, there's my name there. So this is the first thing I did. I called create node, which made this thing. I pointed my next at null, and I pointed the head at this node. So that is this line of code here. created it, allocated memory, it has mark in it, it's pointed at null, and then the head pointer points at it. Don't know if there's I shouldn't have started a a discussion about. Oh yeah, let's have a big discussion about which animes are superior. That would be a good use of our lecture time. Let's not go into that. William's asking an actual question, which is, in a linked list, the last node is also the first node to be created. Maybe. I'm going to say maybe, because this is one way to build a linked list. But even by the end of today, we should have another way to build a linked list where this is not the case. So in this particular one, I'm showing you the very easiest way to create a linked list, is where you just keep pushing things onto the front of the list, and the rest of them just keep moving along. But let's go into the diagrams. Okay, so the first player was Mark. I've got my head pointer and my null pointer. So the next thing I do is I create a new player here. I'm going to continue with my modification of the diagrams. This works because Tom and I both have short names, so it's going to fit in this diagram without me needing to resize it. So I create this new one here. This one I put Tom in there, and this is the new player that gets created. So this is this function here gets called. So create player gets called here, puts Tom in here, and then the pointer that gets put into Tom's is the head pointer, which means if we look at this, the head pointer and the next pointer are both aimed at the same object. That's what a copy of a pointer is. A copy of a pointer is something that aims at the same thing. Because a pointer is an address, so the head pointer and the next pointer may be in different places. They may be different variables entirely, but they're both aiming at the same thing if they are equal. So two pointers that are equal are two pointers with the same address. Pointers with the same address means they aim at the same object. I don't really want to use the word object. The same memory location, because object is like, it's got so many connotations in other programming languages. Okay, so this one has been created, and its next points at the first player that I created here. And so these two are starting to chain together. This is not a full linked list yet because we don't have access to Tom's node yet. But next, I shouldn't say the word next either. There's just so many keywords. Okay, what we do after this is we then move the head pointer to the node that we just created. This is this part of this line of code. So after we've called create player, we could move the head pointer by assigning the head pointer to the address that gets returned from this create player. And so that's what happens here. Just going to edit these again. The head moves from where it was. It was pointing at first player. It is now pointing at new player. And note this structure now has a head pointer pointed at the first element of the list. And the first element just happens to be the newest element of the list. And then its next pointer points at another element of the list. Its next pointer points at null. This is now a fully formed list. We could have more nodes after this, but so long as the last one points at null, this is a fully formed linked list. So this is the easiest possible way to build up a linked list, because all you need is a function that creates a new node, and you can build up a linked list. It's limited in that you kind of have to make things in this reverse order and put them together, but you can still build up a linked list in a really simple way, like this. For us to test whether this linked list is working, we're going to want to loop through this list and print out everything that's in it. So this is a function that we've looked at last week, and this is the basic looping through a list function. And what it's going to do is say, all right, give me the head of the list, and I'm going to loop through the list and print out their names one at a time, and then we'll be able to see what's in the list. So let's make this function, let's build up a list using this kind of setup, and then we'll be able to see what it prints out. Okay, so you know what I'm gonna do? I'm just gonna copy the rest of this code here so that I don't have to type it all in. There you go. So we are hopefully creating a list here, but we don't know whether it's working or not. because all we know is that, yes, we've called this function multiple times, but until we can actually print out the list, we don't know whether it's working or not. So let's have a print function. I'm going to assume it's void because it's probably not going to need to give any information back. Print players. Did I call it print players in the slides? I did call it print players, good. All right, print players is going to need the head of the list to be able to start printing, which means it's going to need a player pointer to be able to get the first element of the list. Sorry, someone wants to say hello. That's right, she's just saying hello and going over there. Alright, it's going to need a struct player pointer, and that's going to need to be a pointer to the head of the list. I might even call this head here to imply that the input to print players is the first element of the list. So I'm going to copy that, paste this down here, and say, okay, this is the function that I'm actually creating. And I'm going to give myself some information to remember what this is. Loop through all players in the list starting at head and print out their names. Okay, so what I might do, I mean, if I want to, I could just use head as the pointer, or I could create another pointer in here. I'm going to create another pointer here to make it obvious what the difference is. So I can have a pointer to current, which is the one I'm currently looking at, and I'm going to say that's the head. So we might do this sometimes if we want the head to not change. So we want to keep track of where the start of the list was. I can have a different one, which is like the thing that's going to move through the list. So I'll have one pointer to the start of the list and another pointer that moves through the list, and that's going to be called the current here. So I've got the current pointer, and I've got a while loop. And I'm going to put together the basic structure for a while loop that uses a pointer to a linked list. So while the current is not equal to null, so while I'm pointing at nodes before I've gone off the end of the list, I'm going to loop through, and every time I move from one to the other, my current pointer will get changed to whatever is the next pointer, which is me saying, look in the current node, find its next pointer. This finds the next pointer of the node I'm currently looking at, and overwrite current with that. So it's like current is pointing at this, and I say current equals current next. That's going to move the pointer to something else. That's so weird. I don't know if she actually opened the door then herself, or I didn't shut the door properly. I'm pretty sure my cat can't open the door. Are you coming out? Okay, goodbye. I don't know if she actually wanted to leave the room or not, but the door opened, so I'm letting her out. Okay. Right. So this while loop will go through a linked list. So until we've gone off the end of the linked list to a null pointer, we'll move our pointer along the list. I've got some diagrams of this as well. Actually, do I have diagrams of this one? I think I have diagrams of this one in last week's lecture, so you can go back and have a look at that if you want. So in here is the actual work that we're going to do. I'm going to remind myself of what we've done here and stuff. Have printed out nodes up to current. So anything before current I've printed out. Then I'm going to do a printf here. So back to like the simple code. Remember those simple days when all we were doing is just printing f random bits of information. We're going to print out a string, and that string is going to be the current node's name. I might put an end line after that, so that way everyone gets one line for their names. Okay, so This function is going to loop through the linked list. What it's going to do is it's going to move from one node to the next, and as it moves from one node to the next, it's going to print out the name it sees there. When the pointer equals null, the pointer will equal null. Did we? No, I'm not going to talk about insertion yet. So, the pointer will first be a copy of head, which means it'll be pointed at a new player, and it will say, okay, Tom, I'm going to print out your name, and then it's going to follow the next pointer, and it's going to move along to this one, and it's going to say, okay, I'm going to print out the name here, which is Mark. So what it should do is it should move through this list. The pointer will move from one element to the next through the list, and each time it's going to print out what it finds there. So let's see, because now we should be in a situation where this should work. So print players is going to need to know the list, which means it's going to take as input a struct player pointer, and we have a struct player pointer here called head. So I can give head to my print players, and this should print out this list as we've created it. So now we're actually in a position where we can test this, which is important because we've written a lot of code here, and we want to make sure this works. So let's come across and edit. Oh, sorry. Not edit, I was just reading the line above. Compile this battle royale program, and we're going to call it battle. And then run it. And what we have now is printed out a list of the people who are in this particular battle royale. So note that the last time we changed head, it was Master Roshi at the head of the list, and then if we go backwards through the list, these are the things that we'd put into the list earlier, and we just pushed them along and made new heads in front of them, which is why this list ends up in reverse. Let me just show you a little bit about how this works. Okay, so the first one we created, I'm not going to go into too much detail, I want to do this quickly, it was just me. I'm just going to put an M in there for that one. And then the head pointer was aimed at that. The next one we created was Tom. And we don't know where in memory these things are going to get created, so I'm just going to put it here. Tom was here, and then Tom's next was aimed at me. And then the head pointer, which is here, was changed, so it was no longer aimed at me. It was aimed at Tom. The next person who got created was Goku. I'm going to put him over here. And memory allocation kind of works like this, is that your computer will find the next piece of available memory and say, okay, here, this is your piece of memory. I mean, often these are going to end up right next to each other, but I'm just going to put them in random places in this diagram to show you that we have no guarantee of where these things are going to be. So Goku gets created, and Goku's next pointer pointed at Tom. And then the head pointer was then moved to Goku. Like so. Like that. So this is how we were building up our list, which is why the list ends up in a reverse order when we print it out, because head will point at the most recent one, and then it will point at the one before it and the one before it. This isn't the only way to make a list. This is just the easiest way to make a list if we only have a create player function, and the print players function is just showing us that. So this is really just us having the create player function, calling it multiple times, and just changing where the head is every time we add something onto it. That's weird. Why did we go up to 200 viewers? Has this been slowly climbing? Is everyone just like from the course? James just noticed this viewer's just boosted. I hope we haven't just been promoted by YouTube to be somewhere else or something like that. That would be really weird. Yeah, AA, exactly. We're constructing the linked list from the last node and then adding nodes in front of it as we go along. So every time we create one of these nodes, it becomes the new head, and the rest of the list continues on the... Oh, Andrew, okay, thank you. Well, I mean, I guess that's good, because if we were in person, I would expect usually at this stage of term to still have sort of 500-600 people, um, and that's where we're supposed to be at. So like I think that at the moment, with with everything going online and people watching things at the time where it's available to them, we're not going to have as many people as we would normally have in person. Okay, so let's continue with what we're doing here. So we have built our list like so, and we have the ability to print it out. So as we see, that's not necessarily the only way that we want to create a list. Maybe we want to be able to insert people in different points in this list. So let's think about the idea of inserting nodes in between other nodes. This is interesting because now we have the idea of doing something that an array could never do. So inserting elements in between elements in an array, we can't just squish something in between. To insert something into an array in between other elements, we would have to grab everything that's in an array, copy it all one further along, and then put the other element in. It's a bit fiddly, but with a linked list, we can do this by moving pointers around. So this slide shows you the recipe of what to do, but what I will probably do is show you the diagrams instead, because this can be a bit fiddly. So we're going to do this by aiming pointers around. So we're going to make a new node, and we're going to take the nodes that were meant to be before and after that node, so the nodes we're squeezing something in between, and we're going to move the pointers around between them so that the nodes end up in a complete chain. So Tom's seeing a bit of spam there. We're not even sure if this is actual students or not. So if people are posting stuff, please keep stuff on topic to what we're actually talking about. So maybe there are people here who aren't actually part of the course. I may end up making the live streams not public if we continue to get people who are just hopping in and spamming, but we'll see how we go. Yeah, because it seems like some people are not necessarily students. So if that happens, I will make them unlisted and only students will get the link to it. Yeah, thanks, Tom. Yeah, we'll figure that out after this, because we haven't usually gone up to this many concurrent viewers, so it seems a bit sus that the students would suddenly change their behavior, especially for a 9 a.m. lecture. This is the one there's usually less people in. Okay, back on topic. Inserting nodes into a linked list that already exists. So let's look at a linked list that already exists. We've got a first node and a second node here. That's really awkward with those numbers being like. Anyway, doesn't matter. We're not worried too much about what's the data in these. But here is a linked list that already exists, and now we want to think about the idea about what happens if I want to insert a node in between these two nodes. So instead of only being able to insert things at the front with the head, I want to be able to put things in between the first and the second node. So first thing I'm going to need to do, I'm going to need to create a new node, right? So I haven't done anything to the list yet. I've just created a new node. It doesn't matter what data's in these for the moment. We're looking at the structure of how we insert things. So I have a new node here that may or may not have some information in it yet. But in order for us to make this node part of this linked list, I need to set up these pointers so that everything is joined together the right way. So first thing that I do with this new node is I say there are two nodes in the list that already exists. There's the one node that's before me and the node that's after me. There are examples of us also adding things on the end and adding things on the front. You've actually seen how to add something on the front already now. Adding something on the end we can also do. It's a little bit simpler than what we're doing now. But I want to show you this case because this is the one that we'd be using most often. So I've created my new node and I want it to point at the second node and I want the first node to point at it. So what I need to do now is to move these pointers around so that these things are all connected. So the next thing I'm going to do is I'm going to say there's a node that was before me. If there was a node that was before me, I want to copy its next pointer. If I copy its next pointer, I am now connected to the second node, which means there's a chain here that's going and I'm connected to that chain, which is good. Yeah, someone is spamming comments there as well. Um, hmm. Tom, I'm not sure if you can remove those comments or not. Um, yeah. Thanks for being around for this as well, Tom. I wasn't expecting us to ever sort of go viral or anything weird like that. um, okay, so what we've done is we've copied the next pointer of the first node, which means if we've copied it, it means we're aimed at the same place. And now the new node is in the chain to a certain extent. But it's not completely in the linked list itself, so for it to be in the linked list, the first node has to connect to it. The order of doing these things is important, right? Because this next node has to copy this one before we change the first node to point at the new node. So the next thing we do now is we flip the new node's pointer, the first node's pointer to the new node. So now we have a head pointer pointing at our first node points at the thing we've just inserted, and the thing we've just inserted, its next points at the second node. So now we have a chain, and now we're back to having a fully functional linked list that says I've got a pointer to the first node, and then each of these nodes' next pointers point at the next node in the list from them, and they're all joined up, which means I've made this new node and I've been able to move the pointers around to connect all of these things together. So we have some code here for insertion of players into our game in between other nodes. What I'm going to do I'm going to leave this here for reference because this is going to be really similar to the code that I'm going to write. But what I'm going to do is actually write the code bit by bit so you can understand what I'm doing with it. Where are we? Over here. Okay, so I'm going to create a new function here. It's going to be called insert player, and it's going to take two pieces of information. Francis is asking about where we find the lecture slides. The slides are on our WebCMS in the lecture section. So these actually went up yesterday, the slides that I put up, so they should be available for you there. Which is a test. If you are one of our students, you have access to this. If you aren't one of our students, then you don't. Yeah. Apparently 240 is enough to be going viral. Yeah, the viewers are jumping up a fair bit. So let's see. Okay, so let's make this insert player function. So there's a couple of things that we want to do. First thing is I need to know what kind of output this function is going to have. What I'm thinking that the best thing for this output to be is it's going to return the head of the list. So I'm going to give it the head of the list, and it's going to return the head of the list to say that this is still the same list. This is going to be important because what if I insert something into, say, an empty list, or I insert something as the start of a list? So I want to be able to return the head of the list, which may not be the same as the head of the list that had been before. So I'm going to return a struct player pointer from this. I'm going to need two pieces of information. One is the list as it currently exists, and the other is the... Oh, I wonder if we're going to create this from scratch. Maybe we're going to create this, in which case we're going to get the name of the node that we're creating. So I'm going to give it the same name that we gave it before, which is a string new name, which is going to be the information of the new node that gets inserted. And this is going to be... Did we have the head as well? Ooh. No, we're doing this in a simpler way. Okay, so we're not going to do it with the head. We're going to do it with an insertion point. Right. Okay, let me start writing this code. I'm just going to make sure it's as close as possible to what I was doing in the slides. So we have a point that we're inserting in. The point that we're inserting is this node here. So we have a node, and we're saying insert after this node. So we have a pointer that is most likely pointed at a player. It might actually be null because there might be no players in the list. And then we're going to do is we're going to insert after that one in the list. So let's go back to the code. Copy this and say insert a player into a list of players. We're going to insert after the insertion point player, and then we're going to return I think that we are returning the insertion point, or we're going to return a pointer to the player itself. I think I know why I have this return in here. So we're going to return the insertion point unless it was null, in which case we return a pointer to the new, oops, autocomplete there, the new player. Alright, this is what I'm guessing that I was doing here, which I'm pretty sure is, and it makes sense to me. So, if we were to insert into a list that was empty, if we were inserting into a list that is null, then there's no way for us to track where this thing is gone unless we return the pointer to it there. Oh wow. Sorry, Tom. Thank you for dealing with this. We are not going to go public anymore with our lectures because it seems like we found some random spammers today. Yeah. Apologize to everyone. We will hopefully not have this problem in the future. I'm going to keep coding. Please don't look at the comments for now. I mean, you're on the internet, so you don't look at the comments. Right. Yeah, thanks. Okay, Tom's going to mute anything that it isn't specifically a question for the course now. Thanks, Tom. Sorry about that. All right. We're going to continue actual coding, and I'm going to try not to look at the comments until the end, and then we'll take questions and things. Okay, so if I'm going to insert a player, first I'm going to follow the steps here. So the first thing I was going to do is create a new node. So I'm going to create a new node, and that's easy because I have a function to do that for me. So I'm going to make a pointer, and I'm going to call this the new player, and I'm going to call create player. Create player is going to it's going to need a string for the name, which I've been given here, which is the new name, and the first input is that, so I'm going to call that new name. And for the moment, I'm going to make it null because I don't know what it's going to connect to. So I'm going to figure out what it's going to connect to, and then I'm going to assign this pointer. So, two cases that we can have here. The list is null is one case, and the insertion point is a node is the other case. Because there's two possibilities here, right? One is I'm inserting into a list that doesn't currently have anything in it, which means that this pointer that I've been given is null. If it's not null, then I'm going to follow this procedure, but if it is null, it means I'm inserting into an empty list. So I need to test for that. So if and else, I'm going to put this in here and this in here. So this is like, I think I was talking about this before, where sometimes I'm going to write comments before I write code, and then I'm going to structure my code around those comments. So if the list is null, that means insertion point that I was given is null. The important thing is, if insertion point is null, then I can't start trying to get information from the insertion point because it's not a node. It doesn't exist at all. So if the insertion point is null, there's a certain thing we're going to do. I'm going to skip over that one for now and come back, because if the insertion point is a node, this is the code that matches our diagram itself, and so we want to look into this. So the first thing I'm going to do is I'm going to copy the insertion point's next pointer and make that my next pointer for the node that I've just created. So my new player next is going to become a copy of the insertion point's next pointer. So this is me saying, take whatever was in the insertion point's next, and now that becomes my next. That's this step here. So going from here, where this was null, it didn't have anything in it. Well, it did, it was pointed off to null. Is now a copy of the insertion point's next. Next thing we're going to do is take the insertion points next and now aim it at myself. Now that I don't need it to skip over that anymore, I want it to be aimed at myself. So the next line of code is to say that insertion point next is going to now point at the new player itself, because the new player is also a pointer, so I can copy that. So all the stuff that was happening in those diagrams here, so created, then I've copied the next pointer from the first node, and then I've moved the first node's next to aim at my new node. So now I've got this situation where with those steps, I'm all connected up. So what we get is, if the insertion point, I'm just going to put a space in there, so I don't have anything in here yet. If the insertion point was a node, I am able to access its next pointer and get a copy of it, and then I'm able to replace its next pointer with the pointer to myself, and that's going to join up insertion point into the list. Sorry, not insertion point, new player into the list. One thing that that I haven't pointed out, which is actually really cool about this, is if insertion point was the last node in the list, so if insertion point was at the end of the list and its next pointer was null, then new player next is just a copy of insertion point next, which is null, and insertion next points at new player. This actually is already covering the case where it's inserting at the very end of the list. It's also inserting in the middle of the list, and it's inserting at the end of the list. So this piece of code can add a node to the middle of the list or to the end of the list. Now I need to deal with the situation where if I'm inserting into a list that doesn't have any nodes in it yet. So a pointer to null could be considered a linked list with no nodes. So if this is a linked list with no nodes, then what I'm going to do is I'm going to say that the new player pointer is the entire list. So let's go. Yeah, I actually don't need some of this code here. I'm trying to figure out what I was actually trying to return there. I haven't changed all my code here. Hang on a second. I changed the name of some of this stuff in this slide, and I was like, why is this called list node? And why is that? Alright. Yes. Sorry. I changed this slide to rename some of the variables, and I hadn't actually changed it. Okay, so what we're going to do is, when we're finished with this, we're going to return the position that we inserted from. So we're actually returning the insertion point. But if the insertion point was null, we're no longer returning the insertion point. What we're going to do is we're going to say that the insertion point is now equal to the new player. So in the case where the list didn't exist before, now the list does exist. And so if the list does exist, it's pointing to the new player. Otherwise, we just return the same thing that we were inserting from before. So if this was the head, it's the head, and if there's a new head, then it changes to something else. So if I was always inserting after the head of the list, then either I would get a new head here if the list was empty, or if the list was not empty, the head stays the same every time. Sorry if that's a bit confusing. I was even confusing myself as I was going there. William's asking an interesting question. If you are shifting around nodes in the list, would it be a similar concept to inserting? Yeah, if I were to move something from one part of the list to another, I would actually do a removal and an insertion. We haven't done removal yet, but you can kind of, if you think about this theoretically, think about how you would remove something. We're going to talk about it in detail later. So let's have a look at this insertion in action, where now instead of this using create player to add things to the list, we're going to insert things into the list. So let's just, I'm going to move that stuff down there and say the list starts as null. And then I'm going to call insert player to add someone to the list. So I'm going to say the head is now going to be equal to insert player. The insertion point is the head, and the new name is Mark. So we don't have that anymore. I'm just going to comment these out. So what this one is going to do, because the head was null here, what it's going to do is it's going to trigger this if statement and say, okay, make the new one. It's pointed at null in its next, but it has the name Mark. And then the insertion point becomes the new player. So what I've said is insert into an empty list, and if I insert into an empty list, then I become the new list. Now that I have a list, I can insert again. So this is me saying insert after a certain point in the list. So the head pointer is pointed at me, so I'm saying insert after me. So if I'm inserting after me into this list, I can put, let's put Tom. Oops. Tom in there. And then I have the head of the list is going to remain the same, because this time I triggered this else statement because it was not null. And so I would now insert after the head, so Tom will be the second element in the list. And if I want to, I could keep calling insert player and inserting things just after the head of the list. This is not my final form. This is not the final thing that we're going to be doing with insertion, because the next thing we're going to do is insert things into random places. We're not really going to get time for that today, so we'll be doing that tomorrow. But at least I want to show you some more inserting into the list like this. So I've done Tom. Let's insert the other three. Insert player after the head. And that's going to be Goku. Oops. And we're going to do the same thing for Bulma and Master Roshi. What I might also do is show you this as it's running. Okay. So it's pretty simple. It's actually not that different from the create player. The only difference is I make myself the head, and then after that, I'm inserting players after me every time. This is because I don't actually have any particular pointers to anything I want to insert after, so everything's getting inserted after the head. So the reverse list is just after me, and I'm the first element of the list. So what we might do is show you what's happening at each stage. So let me compile this, see if it compiles. Okay, that's good. This just says my name, because what I've done is I've made a list which is null. So the list has no elements in it, and I've inserted one element into that list, and then I've printed it out. So I'm the only element in the list, my name is the only one that comes up. Next, we'll insert someone after the head. So inserting someone after the head is going to be different from the order that we had before. Tom should come after me now, because I've said I'm the head of the list. Now Tom is inserted after that head of the list. I'm saying the head equals the result of this. Remember that this function was going to return the insertion point. So if I say the head is the insertion point and the head was a valid head, it wasn't null, it's just going to give me back the same head. So here the head's not actually going to change, it's going to remain the same, it's going to be me. So let's compile and run this, and we'll have a look at how it goes. Right, so there's me, and then there's Tom. Now it gets more interesting when I add a third person to this. So a third person is inserting Goku. So this is exactly this situation now. I have one node and another node, and I'm inserting after the first node. So I'm inserting a new node after the first node. So what I'm expecting as a result of this is I go first, then Goku, then Tom. Because my program, my function to insert the node is going to move these pointers around to make Goku the second one, because I've said insert after head. So if head is still me, insert after head should put Goku between me and Tom. So let's run this and see what we get. I'm going to compile that again and run it. Cool, it's done what I've wanted to. So now I have the ability to insert in between two. And if I'm inserting after the head again and again, what it's going to do is it's going to keep putting these people into the second place, and the others are going to move down the list. So let's compile this and run it. Right, so Tom, Goku, Bulma, and Master Roshi all ended up in there in reverse order. Now we're not too worried about this just yet, because everything that I've done here is just to insert after me. So every time I put someone in, I put them in the spot after me. But what we're learning about here is the ability to move the pointers around so that things can be inserted in between elements of the list. So let's see some of the questions I think that are coming up, because we should finish now. So it's time to finish and let everyone go off to their tutorials. But if anyone wants to stick around to ask some questions and get them answered, I will answer some questions. I think Michael here is answering some questions as well, but we'll see what we've got. So, oh, there's lots of questions. Simply me, Joe. I'm just coming back here to look at things, so hopefully I'm not answering something that's already been answered. Why aren't we freeing any of these? The reason is because I don't have enough time to show you that right now. I am definitely going to show you how to free these later, and also how to free an entire list, because it's not trivial to loop through and free an entire list. So at the moment, yes, this is leaking memory. Every time I run this, there's still some memory in that we're using. However, our operating systems are smart enough that when our program finishes, it says, okay, all the stuff you allocated goes away. You're not going to get to do this. So the program can only screw up its own space for now. So yes, I should have freed all of these after I finish using them, but I haven't yet. We will definitely do that tomorrow. So I'm not leaving this as a memory leaking program. We will be doing it tomorrow. Okay. New player is created by a malloc. New player, I assume we're talking about here. Yes, it is created by a malloc because it calls this function. So the question was, is new player created by a malloc? It calls create player. Create player will then jump in here. Create player will call a malloc. So this function here is technically allocating memory because it's calling a function that allocates memory elsewhere. So yes, we will be allocating some memory. Simply Mijo is asking if the computer memory will be filled if you run that code several times. Kind of. But no. Actually, no. Running this program multiple times will not fill up your memory, because every time this finishes, your operating system will be like, hey, you left all this garbage behind. I'm going to clean this up for you. So our operating systems are smart enough that they clean this up for us. Francis is asking, is insert player a node or a function? So insert player is a function. We know this because it has these brackets here for input, and it has code that it runs. It runs information, but it will return a pointer to a player. So it will make a player, and it will return a pointer. If the list was null, it'll actually return a pointer to that player itself. If the list wasn't null, it will add something to the list, and then it will return back the pointer to the insertion point that it was given to add something to. So it's a function, but it's a function that creates a pointer, creates a struct even, and a pointer to the struct. It will return a pointer to a player. Simply Mijo had it there. Yeah, it's a function that returns a pointer to a struct player. Yeah, that's it. Paylong Lady is asking, is insertion point the address of the node that we need to insert after? Why in line 61 it isn't insertion point next is not equal to null? So let's look at the sign. Okay. So insert player gets given a pointer, and we say we're going to insert after that node in a list. The reason we're checking for null is if we're inserting after a theoretical node, but that theoretical node doesn't exist. So if we're given a list that is empty, if we're given a list that's empty, then insertion point will be null. So the entire list was empty. There were no nodes. So this is us working with the idea that we can get given insert player on something that doesn't have a node. I'm not sure if we're going to get some frame drop at the moment because my upstream just slowed down massively. Oh well, we'll see how we go. Hopefully the audio still comes through. So if the insertion point wasn't a node, then we need to check if it wasn't a node. If it is a node, then this code works. So we need to check that it's not null before we can access its fields. Because if we get given a null insertion point, we won't be able to access any of these fields here to move pointers around. We'll have to create a new list with it. Yes. Oh, you worked this out yourself. Great. I'm glad that you got that. Calvin's asking, why do we create pointers in lists? We use pointers, not pointers after we created it. I remember we need to use star pointer when we studied pointers. Calvin, I'm not entirely sure what your question is, but maybe you're asking about whether we're creating these and why we are creating these as part of the structs. The pointers in the structs are all there to connect the nodes together. I apologize if I'm not sure I understand the question entirely here. So you're asking why we were creating these pointers. It's because with these pointers, each of our nodes is then connected to each other for us to use them. So I'm not sure if that's exactly what you're asking. Oh, right. Why are we not using something like star pointer here? So if I put a star on a pointer that exists, that's me going to the memory location, looking at the values that are there. So if I put a star on this is saying I'm looking at the actual struct that new player was when it was created here. But I'm not trying to work with the struct there, I'm trying to work with the pointer itself. So if I'm working with the pointer itself, I don't put the star on it. The star is an actual action on that pointer which says follow this pointer to where it's aimed at, and then look at the information that's there. And since I'm not looking at the information here, I'm actually looking at the pointer itself. I'm saying I'm supposed to return a pointer, and I'm going to return the insertion point. I'm going to overwrite that with this pointer. So I'm not worried about what it's aimed at the moment. I'm worried about the address itself, because that's the thing I'm going to return. So that's why in here I'm not using a star. However, in here I am kind of using the star, because remember that the arrow here says follow this pointer to its struct and grab one of the elements, one of the fields inside the struct. So this code here is roughly the same as this code to say follow the pointer to its location and then grab the thing that's inside it. It's just a different notation. This is the common notation for grabbing a field inside a struct that's been pointed at by something. So hopefully that answers you. I think I understand your question now, Calvin. I hope I'm answering that. Simply Me Joe is asking the difference between type defing in a header versus creating a structure inside the C file. So this is about accessing fields. Yeah, this is definitely about accessing fields, but you didn't understand it last time. We're definitely going to cover this again. When we type def in between files, what we're saying is there's a structure in another file that you can't see. So because there's a structure in another file you can't see, you're not allowed direct access to it. But if I give you a pointer to it and some functions, you can give that pointer to the functions. We type def that as a new type. What that means is, for example, in the Batman example, I was not allowed to just delete Batman's powers. Like, I don't have the ability to just remove superpowers from Batman, because no one's taken that voice away from him. The gravelly Christian Bale voice, if you remember. You can go back and watch this if you're looking for it. So I don't have the ability to access the fields of the struct and change them, but I can call the functions that say add powers. So this is our way of saying you can know that a structure exists, but you can't know what's inside it. And this keeps the data inside that structure safe, and I say the only way you can access the fields in that data is by calling the functions that I say you can call. So you can only call these specific functions, and then you can access what's inside there. But you never get direct access to it, which means you can never make any mistakes and delete that data by accident, or you can never change that data in a way which I consider to be not legal to the way the data structure should work. So the difference between declaring a struct like this here and having a separate player file that has the struct, and this C file wouldn't see the struct, which means all I'd be able to do in my main is call these functions, which I have been doing, but I would never be able to do something like head name is something else, or string copy something else in there, because I wouldn't have access to the head name. And that way I can protect my data. So doing the type def and splitting things into separate files stops someone from accidentally doing something like this and changing things. Because what's much worse than that is me doing this. If I said head next equals null, it's going to cut off all of these other nodes that I put in there, and I'll be the only one. I might want to do that. And I can do this because I have access to it. But if I didn't have access to this struct, and instead I only had a type def, I would not be able to write this code, which would be great, because that means that my structures and my linked lists are safer because they're protected behind the type def and behind the fact that we have a separate file and you can't see what's in that separate file. So that's the reason why we would do something like a type def. Abraham's now being suspicious that people are not students in the course. Oh wow, okay, so John, you actually just happened across this live video. I think actually, if you look up the subject, which is COMP1511, you might be able to get to our web CMS, which is a content management system for the University of New South Wales, which is what what this lecture is for. And I'm pretty sure my lecture slides are public there, so you still actually might be able to get access to it. So if you look up the web CMS for COMP1511, you could look across it. So if you're interested, John, I have no problem with you sticking around and watching. We don't usually lock the doors on our lecture theatre either. It's just usually a little bit more difficult for people to turn up. We just had some problems today because we had a lot of random spammers come in, and that was not very pleasant. So we're probably not going to be public in the future. So I apologize that this may be the last time you see it. But I may make the videos public after the fact, but the live streams themselves will just be for students. Oh, cool. All right, John, so you can still see it. All right. Okay, I think I've covered all the questions that are there. I should head off. A bunch of you probably have to go to tutorials now anyway. So I'm going to sign off here. I'll see everyone tomorrow at 11 a.m. for the next live stream. I will put the link on our web CMS, but I probably won't make the live stream public. So it'll only... so for people like you, John, who are just the general public who are interested in seeing this, you'll get to see the video afterwards, but I'm going to reserve the stream itself for the students enrolled in the course. Or, Tom, we can just restrict the chat. We could just moderate the chat, but that might mean that you will have to be moderated all. We'll sort something out to deal with the spam anyway.